Venus spins backward. The sun would rise in the west and set in the east. A planet, nearly the size of Earth, turns the opposite way, and its day lasts about 243 Earth days, longer than its year of 225. That is not a curiosity. It is a record of torque, impact, and atmospheric forces acting for billions of years. Tonight, we examine angular momentum, radar measurements, thermal tides, and competing gravitational effects that may have reversed an entire world. Stay with me as we begin. Why does Venus spin backward? What force was strong enough to reverse an entire planet? A planet nearly the size of Earth rotates the wrong way, and that single fact forces us to rethink how stable a solar system really is. Venus spins in retrograde rotation. If you stood on its surface, the sun would rise in the west and set in the east. Its sidereal rotation period is about 243 Earth days, moving opposite to most planets, while its orbital period around the sun is about 225 Earth days. In a system born from a rotating disk of gas and dust, where angular momentum sets a preferred direction, how does a world end up reversing that inherited motion? To approach this carefully, we begin with angular momentum, the conserved quantity that governs rotation. When the solar system formed about 4.5 billion years ago, a collapsing molecular cloud flattened into a protoplanetary disk. Observations of such disks today with the Atacama Large Millimeter Array and the James Webb Space Telescope show coherent rotation patterns. Planets forming within that disk inherit the same overall direction. Earth rotates prograde. Mars rotates prograde. Jupiter rotates prograde. The default pattern is not accidental. It reflects conservation of angular momentum in the original nebula. Venus stands as the major exception among the terrestrial planets. The spin of a planet can be described by its rotational angular momentum vector. Reversing that vector requires either adding enough opposite angular momentum to flip its sign, or gradually breaking the original spin down to zero and then pushing it in the opposite direction. Both options demand significant torque. A torque is a force applied with leverage. Over time, torque changes rotational motion. The question is not whether physics allows this. It does. The question is how much torque is required, over what time, and from which mechanism. Early measurements of Venus's rotation came from radar observations in the 20th century. In the 1960s, radio astronomers such as Gordon Pettengill used radar reflections from Arecibo Observatory to determine that Venus rotates slowly and in retrograde. Later, NASA's Magellan mission, launched in 1989, mapped more than 90% of the Venusian surface using radar imaging. Magellan confirmed the rotation period and provided high-resolution surface data. These measurements are not speculative. They are grounded in precise Doppler tracking and radar echo timing. The planet truly spins backward relative to its orbital motion. One possible explanation is a giant impact early in Venus's history. Planet formation models show that during the late stages of accretion, protoplanets experienced collisions with bodies comparable in size to Mars. The widely accepted model for the formation of Earth's moon involves such a collision with a body often called Theia. Numerical simulations demonstrate that oblique impacts can dramatically alter spin states. If a sufficiently massive object struck Venus at the right angle, it could slow its original prograde rotation and potentially reverse it. This idea is attractive because it mirrors events known elsewhere. Yet it raises further scrutiny. Earth's giant impact left behind the Moon and specific geochemical signatures in isotopic ratios. Venus has no large moon. If a collision rewrote its angular momentum, what evidence should remain? One might expect large-scale crustal asymmetries or distinctive impact basins. However, Venus's surface has undergone extensive volcanic resurfacing. Magellan data suggest that much of the surface may have been renewed hundreds of millions of years ago. Volcanism can erase earlier impact scars. The absence of obvious scars does not eliminate a collision scenario, but it complicates the forensic trail. Another pathway avoids catastrophe and instead relies on persistence. Over billions of years, small talks can accumulate. Venus possesses a dense atmosphere composed primarily of carbon dioxide, with surface pressures around 92 times that of Earth. Solar heating creates atmospheric tides, pressure bulges that shift relative to the planet's surface. Alexandra Correa and Jacques Lascar developed detailed dynamical models showing that thermal atmospheric tides can exert long-term torques on a planet's rotation. These torques arise because the heated atmosphere does not align perfectly with the Sun. Friction and gravitational interactions create a phase lag, generating a steady mechanical push. The strength of this torque depends on atmospheric mass, solar flux, and the planet's rotation rate. Venus, receiving intense solar radiation and hosting a thick atmosphere, becomes an efficient candidate for such a mechanism. Over time, solid body tides raised by the Sun tend to slow rotation towards synchronous locking. Meanwhile, thermal atmospheric tides can push in the opposite direction. Under certain conditions, the balance of these competing torques yields a stable retrograde state. No single moment of violence is required, only sustained interaction over geological timescales. NASA's planetary science summaries often emphasize how Venus challenges assumptions. In one official overview, NASA describes Venus as a planet that rotates backward compared to most other planets in the solar system. The language is simple, yet the implication is profound. The mechanisms shaping rotation are diverse. Angular momentum is conserved, but it can be redistributed between solid body and atmosphere. Recent radar studies have added a new dimension. Jean-Luc Margot and colleagues used radar speckle tracking from Earth-based facilities to measure subtle variations in Venus's rotation rate. Their findings suggest that the length of day can vary by approximately 20 minutes over time. Margot noted, "That probably explains why previous estimates didn't agree with one another." The variability indicates active exchange of angular momentum between the atmosphere and the solid planet. Venus is not a static relic. Its rotation remains dynamically coupled to atmospheric motion. Consider the scale involved. The moment of inertia of Venus, determined from gravity measurements and rotational dynamics, indicates a differentiated interior with a metallic core. Altering the rotation of such a massive body requires transferring enormous angular momentum. Yet the atmosphere, though thin compared to the whole planet, moves at high velocities. Cloud tops circle Venus in about 4 Earth days, a phenomenon called superrotation. Momentum stored in those fast-moving layers can couple through friction and pressure gradients to the surface. Over long durations, even modest torques can reshape spin states. If a giant impact flipped Venus, the change would have been abrupt and dramatic. If atmospheric tides drove the reversal, the change would have been gradual and methodical. Which scenario better fits available data? Impact models must account for present-day interior structure and lack of a large satellite. Tidal models must reproduce the exact rotation period and its stability. Both approaches rely on conservation laws and measurable parameters. Neither rests on speculation alone. Both draw from simulations grounded in celestial mechanics. The broader implication touches solar system formation. Observations of exoplanets reveal a diversity of spin-orbit alignments, some dramatically misaligned with their stars. Venus demonstrates that even within our own system, rotational outcomes are not predetermined. A planet's final spin state records the cumulative history of collisions, tidal forces, atmospheric dynamics, and internal structure. In this sense, retrograde rotation is not an anomaly, but a data point. What strengthens the discussion is convergence of evidence from multiple sources. Radar mapping from Magellan, Earth-based radar speckle studies, gravitational field analysis, and dynamical modeling all contribute pieces of the puzzle. No single dataset closes the case, yet each constrains the possibilities. The mass distribution inside Venus affects its response to torque. The thickness of its atmosphere influences tidal efficiency. The absence of a moon narrows impact scenarios. Step by step, constraints accumulate. When examining planetary angular momentum, it helps to compare numbers. Earth's rotational angular momentum is about 7 times 10 to the power of 33 kilograms square meters per second. Venus's value differs due to slower rotation but similar mass and radius. Reversing such a quantity requires adding an equal amount in the opposite direction. A Mars-sized impactor traveling at typical early solar system velocities could, in principle, supply comparable angular momentum. Alternatively, solar tidal torques integrated over billions of years can gradually remove and redirect spin. The arithmetic is demanding, but not impossible. There is restraint in the data. No current model claims absolute certainty. What exists instead is a narrowing corridor of plausible mechanisms. Each year, refinements in interior modeling and rotation measurements reduce uncertainty. Future missions, including NASA's planned Veritas mission no earlier than 2031 and the Da Vinci mission in the early 2030s, aim to refine gravity field measurements and atmospheric composition. These missions may tighten constraints on moment of inertia and internal layering, indirectly informing rotational history. Venus spins backward. That fact remains firm. The pathway remains open to examination. Was it a single oblique impact in the chaotic youth of the solar system, or the patient work of solar heating and atmospheric tides over billions of years? The evidence does not yet close the file. It invites deeper measurement, sharper modeling, and closer comparison with other terrestrial worlds. And when we look more closely at how long Venus takes to complete one rotation compared with its journey around the Sun, another structural clue begins to surface, one that reshapes what we even mean by a day on that world. How can a day on Venus be longer than its year? What does day even mean there? A planet that finishes its journey around the Sun before it completes a single turn on its own axis forces us to reconsider what we mean by a day. Venus takes about 225 Earth days to orbit the Sun, yet it requires about 243 Earth days to complete one sidereal rotation relative to the distant stars. The rotation is retrograde, opposite to the direction of most planets. Already, the geometry is unusual, but the true complexity appears when we ask a practical question. If you stood on the surface of Venus and waited for sunrise to return, how long would that interval be? To understand this carefully, we distinguish between two clocks. The sidereal day measures how long a planet takes to rotate once relative to distant stars. The solar day measures the interval from one sunrise to the next, determined by the combined effects of rotation and orbital motion. On Earth, these numbers are similar because Earth rotates much faster than it orbits. On Venus, the relationship is inverted. The planet turns slowly and in the opposite direction to its orbit. Orbital motion and retrograde rotation combine into a new rhythm that is neither intuitive nor simple. Radar observations provided the key to measuring Venus's true rotation. Because thick clouds obscure its surface in visible light, astronomers relied on radar reflections from Earth-based observatories. In the 1960s, precise timing of radar echoes revealed the slow retrograde spin. Later refinements, including measurements from NASA's Magellan spacecraft in the early 1990s, confirmed a sidereal rotation period of approximately 243 Earth days. These values were not inferred indirectly. They were derived from tracking identifiable surface features in radar maps and measuring Doppler shifts with high precision. The data anchored the discussion firmly in observation. Now consider how sunrise behaves under these conditions. Venus orbits the Sun in about 225 Earth days. While the planet slowly turns backward, it is also progressing forward along its orbital path. The apparent motion of the Sun across the Venusian sky depends on both motions together. Because the orbital motion partially cancels the retrograde rotation, the solar day on Venus is about 117 Earth days. That is the time from one sunrise to the next at a fixed location. The result is striking. Although the sidereal day is longer than the year, the solar day is shorter than both. Geometry reshapes time. This can be reasoned without equations. Imagine marking a point on Venus facing the Sun. As Venus rotates slowly backward, that point gradually turns away. But Venus is also moving along its orbit, shifting the direction from which sunlight arrives. The orbital motion changes the angle of incoming light at nearly 1 degree per Earth day. Because rotation and orbital motion oppose each other, they alter the rate at which the Sun returns to the same position in the sky. When the motions are combined carefully, the interval between successive sunrises becomes 117 Earth days. A day is no longer a simple count of spins. It is a calculation shaped by relative motion. The story deepens when we consider observational evidence of day-length variability. Jean-Luc Margot and colleagues used radar speckle tracking to measure Venus's rotation rate with extraordinary precision. Their findings indicated that the length of a Venusian day can vary by at least about 20 minutes over time. Margot explained in public discussion that this variability probably explains why previous estimates didn't agree with one another. The atmosphere, with its dense carbon dioxide layers and high-altitude winds, exchanges angular momentum with the solid surface. The planet's rotation is not perfectly rigid. Even on a world that turns so slowly, subtle exchanges matter. Venus's atmosphere itself presents an additional complexity. Cloud tops circle the planet in about 4 Earth days, a phenomenon known as superrotation. Spacecraft observations from missions such as the European Space Agency's Venus Express revealed this rapid atmospheric circulation. The surface below may take months to rotate once, yet winds in the upper atmosphere travel at speeds exceeding 100 meters per second. Angular momentum stored in the atmosphere interacts with the surface through pressure gradients and frictional coupling. This interaction influences the stability of the solar day over long periods. The sky and the ground are mechanically linked. The geometry of sunrise on Venus would also be visually unfamiliar. Because of retrograde rotation, the Sun would rise in the west and set in the east. The slow pace of change means that daylight would persist for nearly 2 Earth months before darkness returned. Temperatures on Venus remain relatively uniform between day and night due to its thick greenhouse atmosphere, but the illumination cycle itself is prolonged. The sky would change gradually, almost imperceptibly, yet governed by strict orbital mechanics. Historical context adds perspective. When early radar measurements first indicated that Venus rotated backward, the discovery challenged existing assumptions about planetary formation. Many expected that all terrestrial planets would share similar spin directions inherited from the protoplanetary disk. The confirmation of retrograde rotation showed that rotational outcomes can diverge dramatically. Over decades, repeated observations refined the rotation period to a precision of fractions of a second per Earth day. Each refinement required careful signal processing, correction for Earth's own motion, and elimination of noise from atmospheric interference. The conclusion remained consistent. The difference between sidereal and solar day is not unique to Venus, but nowhere else in the solar system is the contrast so dramatic among major planets. Mercury offers another example of resonance between rotation and orbit, yet its case involves tidal locking in a 3:2 ratio rather than reversal. Venus demonstrates that orbital geometry and rotation combine in ways that produce non-intuitive time cycles. When rotation slows and reverses, orbital progression becomes a dominant contributor to the apparent motion of the Sun. The deeper lesson concerns reference frames. A sidereal day uses distant stars as reference points. A solar day uses the local star. Both are valid, but they answer different questions. On Earth, the difference is only about 4 minutes. On Venus, the difference is measured in months. This contrast emerges directly from measured periods. No abstraction is required. Only careful tracking of rotation relative to fixed background stars and to the Sun's apparent position. The distinction clarifies why the phrase "a day" must always be defined precisely. Measurements of Venus's orbit are equally precise. The orbital period of 225 Earth days derives from tracking the planet's motion relative to the Sun over many revolutions. Observatories and spacecraft navigation systems confirm this value to high accuracy. Combining the two known periods, sidereal rotation and orbital revolution, allows calculation of the solar day. The arithmetic is straightforward once the geometry is understood. When rotation opposes orbital motion, the effective interval between sunrises shortens compared to the sidereal period. The sky becomes a diagram of relative motion. There is also a subtlety involving axial tilt. Venus's axial tilt relative to its orbital plane is small, about 3 degrees. However, because of retrograde rotation, the effective obliquity is about 177 degrees. The axis is nearly inverted. This configuration minimizes seasonal variation while preserving the reversed sunrise pattern. The tilt does not create strong seasonal contrasts, but it completes the picture of how Venus's orientation shapes its time cycles. Orientation and rotation together define climate rhythms. NASA's planetary fact sheet summarizes these values concisely, yet the implications unfold only when the numbers are combined. A year shorter than a sidereal day, a solar day shorter than both. Retrograde motion altering sunrise direction. Variability of minutes arising from atmospheric torque. Each statement is measured and confirmed. Together, they form a coherent mechanical narrative. The planet's sense of time is written in geometry. If one were to design a clock for Venus, it would need to account for orbital motion explicitly. A simple rotational counter would mislead. Timekeeping becomes an exercise in celestial mechanics. On Earth, we add leap seconds to correct subtle discrepancies between rotation and atomic time. On Venus, the discrepancy is fundamental. The rotation itself is slow enough that orbital motion cannot be ignored in defining daylight. The definition of day must be tied to geometry rather than spin alone. Venus therefore becomes an instructive example in planetary rotation, explained through observation and mechanics. It shows that day length is not an intrinsic property independent of orbit. It emerges from the interaction between spin and revolution. The length of day on Venus, often summarized as longer than its year, conceals a deeper structure that only appears when sidereal and solar days are distinguished carefully. The apparent paradox dissolves once the motions are combined with precision. And when we consider that the measured length of a Venusian day can shift by several measurable minutes due to its dense atmosphere interacting with the planet's surface, we are no longer looking at a simple, fixed rotation. We are looking at a world whose spin can subtly respond to real physical forces unfolding above and around it. That is why scientists continue to measure the length of a Venusian day with such precision. Even small differences matter, because they may indicate that the planet's rotation is not perfectly constant, but slowly adjusting over time. Why are scientists measuring different Venus day lengths? Is the planet's spin actually changing right now? A solid planet, nearly the size of Earth, should not casually gain or lose minutes from its day. Yet, precise measurements show that Venus does exactly that. When independent teams compare rotation data across decades, the length of the Venusian day does not remain perfectly fixed. Differences of at least about 20 minutes appear between high-precision estimates. For a world that takes about 243 Earth days to complete one sidereal rotation, a shift of minutes may sound small, but in angular momentum terms, it is significant. Something is exerting torque on a planet whose mass is approximately 4.8, 7 times 10 to the power of 24 kilograms. That is not a trivial push. The method behind this discovery is both elegant and demanding. Earth-based radar observatories transmit powerful radio waves toward Venus. The signal reflects from surface features and returns to Earth. When two separated radio telescopes receive the scattered echoes simultaneously, the interference pattern, known as radar speckle, contains subtle timing information. By tracking how this pattern drifts across receiving stations as Venus rotates, researchers can measure the planet's rotation rate with remarkable precision. This technique does not rely on visual imaging. It depends on coherent radio reflections and careful timing to fractions of a second. Jean-Luc Margot and colleagues applied this radar speckle tracking method using facilities such as the Goldstone Solar System radar in California. Their analysis revealed that estimates of Venus's rotation period differed across observing campaigns separated by years. The variations were not random noise. They reflected genuine differences in rotation rate. Margot summarized the implication directly, stating, "That probably explains why previous estimates didn't agree with one another." Earlier measurements assumed that the planet rotated at a perfectly constant rate. The new data showed that the assumption was incomplete. To appreciate the scale, consider that Venus's sidereal day is about 243 Earth days. If that duration shifts by 20 minutes, the fractional change is tiny, but the angular momentum involved remains enormous. Angular momentum depends on mass, radius, and rotation rate. Venus has a radius of about 6,052 kilometers. Even a slight alteration in rotation speed requires transferring measurable angular momentum between components of the planet. The exchange must involve either external gravitational forces or internal redistribution of mass and motion. The leading explanation centers on the atmosphere. Venus possesses a dense carbon dioxide atmosphere with a surface pressure around 92 times that of Earth. High-altitude winds circulate rapidly, completing a circuit of the planet in about 4 Earth days. This phenomenon, called superrotation, stores considerable angular momentum in atmospheric motion. The atmosphere is not detached from the solid surface. Friction, pressure gradients, and wave interactions couple the two systems. Over time, angular momentum can be transferred between them. On Earth, seasonal winds and ocean currents produce tiny, measurable variations in Earth's rotation rate. Satellite laser ranging and atomic clock comparisons reveal that Earth's day length fluctuates by milliseconds due to atmospheric and oceanic circulation. Venus presents an amplified version of this mechanism. Its atmosphere is thicker, its winds are intense, and its rotation is slow. When atmospheric circulation shifts, the exchange of angular momentum can adjust the solid planet's spin measurably. The principle is identical, the scale differs. Observations from the European Space Agency's Venus Express mission provided critical context. Operating from 2006 to 2014, Venus Express measured atmospheric dynamics, temperature profiles, and wind speeds. Data confirmed strong zonal winds and global circulation patterns capable of redistributing momentum. When combined with radar rotation measurements, these findings support the view that the atmosphere exerts a time-varying torque on the planet. The sky is not a passive blanket, it is mechanically active. External forces also contribute. The gravitational pull of the Sun raises tides not only in oceans, but also in solid planetary bodies. On Venus, solar tides create periodic deformations of the crust. These solid body tides can slightly alter the distribution of mass and therefore affect rotation rate. While the effect is small compared with atmospheric coupling, it forms part of the total torque budget. In addition, the gravitational influence of Earth during close approaches may induce minor perturbations in spin orientation over long timescales. The interplay of forces means that Venus's rotation state is not a frozen relic from the distant past. It remains dynamic. Researchers modeling the rotation incorporate atmospheric angular momentum variations, solar tidal torques, and interior structure constraints derived from gravity measurements. The moment of inertia of Venus, estimated from rotation data and spacecraft tracking, suggests a differentiated interior with a metallic core. Interior properties influence how the planet responds to applied torque. A more fluid core may permit slightly different rotational adjustments compared to a fully rigid interior. Radar speckle tracking has also provided estimates of Venus's axial tilt and precession rate. The orientation of the spin axis affects how solar torques act over time. Measurements indicate that the axis orientation may itself experience small shifts. These refinements help narrow uncertainties in interior models. Each new dataset constrains the system more tightly. There is a historical dimension worth recalling. When early radar observations in the 1960s first revealed retrograde rotation, the priority was determining direction and approximate period. Precision was limited by technology. Over decades, improvements in radio transmitters, receiver sensitivity, and signal processing allowed more accurate determination of rotation rate. What once appeared constant now reveals variability when examined with greater resolution. This progression illustrates how measurement advances reshape understanding without altering fundamental laws. The physical explanation does not require exotic forces. It relies on conservation of angular momentum. When atmospheric winds accelerate in one direction, the solid planet must respond in the opposite direction to conserve total angular momentum of the system, unless external torques compensate. Over time, changes in atmospheric circulation redistribute angular momentum between layers. The result is slight but detectable changes in the planet's spin rate. No violation of conservation occurs, only redistribution. Comparisons with Earth help clarify the principle. On Earth, strong El Niño events alter atmospheric circulation, slightly changing day length by fractions of milliseconds. The effect is measurable with atomic clocks. Venus experiences analogous exchanges on a larger scale relative to its slow baseline rotation. Because Venus rotates so slowly, small torques produce proportionally larger changes in day length. The slower the spin, the easier it is to modify. NASA Planetary Science Communications emphasize that Venus remains an active laboratory. Although no dedicated spacecraft currently orbits the planet, Earth-based radar and previous mission data continue to yield insights. Future missions such as Veritas and Da Vinci are expected to refine gravity field measurements and atmospheric profiles. These measurements will further constrain models of torque exchange and rotational evolution. The case is ongoing. The discovery that Venus's day length varies also influences how researchers interpret historical datasets. Earlier, discrepancies between reported rotation periods once seemed puzzling. The assumption of constancy led to confusion. Recognition of variability resolves that tension. Margot's remark that the variability probably explains why previous estimates didn't agree with one another encapsulates the shift in perspective. Measurement differences are not necessarily errors. They may reflect genuine temporal change. The implications extend beyond Venus. Exoplanet studies reveal worlds with diverse rotation states and atmospheric compositions. Understanding torque exchange on Venus informs interpretation of distant planets observed through transit and radial velocity techniques. A planet's observed rotation period may not be fixed over geological timescales. Atmospheric mass and stellar heating can modulate spin in ways that influence climate and habitability. Venus offers a nearby test case grounded in measurable physics. The fact that Venus's rotation rate can shift by minutes over years demonstrates that planetary spin is not immune to present conditions. It responds to atmospheric circulation patterns and gravitational interactions in real time. A world of immense mass can still be nudged. The nudging is subtle, cumulative, and governed by known forces. The phenomenon is neither dramatic nor negligible. It is measurable. As radar techniques refine further, and new missions deliver higher resolution gravity and atmospheric data, the coupling between sky and surface will be quantified with greater accuracy. The rotation of Venus is not a closed chapter in celestial mechanics. It is an evolving dataset, responsive to forces acting today. The fact that atmospheric torques can shift a planet's rotation by measurable minutes shows that these forces are far from negligible. Over billions of years, such persistent effects could have competed with solar tides strongly enough to keep Venus from settling into tidal lock, as the Moon did around Earth. If tidal forces alone cannot fully account for Venus's unusual spin, then another explanation must be carefully considered. Did a giant impact flip Venus, or would it have left scars we can't find? If a single collision can reverse the spin of a planet nearly as massive as Earth, where is the evidence of that blow? Venus rotates in retrograde and turns so slowly that one sidereal rotation lasts about 243 Earth days. One classical explanation proposes an early oblique impact with a body perhaps comparable in mass to Mars, powerful enough to alter the planet's angular momentum. The premise is mechanically plausible. The solar system's formative era was violent. Numerical simulations of late-stage accretion show protoplanets colliding at velocities of several kilometers per second, releasing energies equivalent to trillions of megatons of explosive yield. A collision of sufficient mass and angle can rewrite rotational states. This idea draws credibility from a known precedent. The widely accepted model for the formation of Earth's moon involves a collision between the proto-Earth and a Mars-sized body. That impact redistributed angular momentum, ejected debris into orbit, and ultimately led to lunar formation. Isotopic analyses of lunar rocks returned by the Apollo missions support the hypothesis of a common origin. The mechanics of spin alteration are therefore not hypothetical. They are demonstrated within our own planetary neighborhood. If Earth experienced such an event, Venus might have as well. To reverse the spin of Venus, the impact would need to counter its original prograde angular momentum and push it beyond zero into retrograde motion. Angular momentum depends on mass, radius, and rotational speed. Venus has a mass of approximately 4.87 times 10 to the power of 24 kilograms and a radius of about 6,052 kilometers. Changing its spin significantly requires transferring enormous momentum. Computer simulations conducted by planetary dynamicists show that off-center impacts can both slow rotation and alter axial tilt. Under the right geometry, reversal is achievable. The arithmetic does not forbid it. Yet planetary science demands consistency across multiple lines of evidence. If such a colossal impact occurred, it should have left signatures. On Earth, the Moon stands as visible testimony. On Mercury, giant impact basins such as the Caloris Basin remain etched into the crust. Mars bears hemispheric dichotomies and enormous basins suggestive of early collisions. Venus, by contrast, presents a more ambiguous record. NASA's Magellan mission, which orbited Venus from 1989 to 1994, used radar to penetrate the thick cloud cover and map more than 90% of the surface at resolutions down to about 100 meters in many regions. The radar images revealed volcanic plains, coronae structures, and impact craters. Surprisingly, the crater distribution appeared relatively uniform, suggesting that much of the surface is geologically young, perhaps resurfaced within the last several 100 million years. If an ancient giant impact left a large basin, extensive volcanism could have erased it. The resurfacing hypothesis complicates the forensic analysis. Venus's surface temperature of about 735 Kelvin and its high atmospheric pressure support widespread volcanic and tectonic activity. Radar observations have identified features consistent with large-scale lava flows. If volcanic episodes flooded the crust globally, impact scars from billions of years ago may no longer be visible. The absence of a visible basin does not exclude a past collision. It raises the question of where deeper evidence might reside. One such avenue involves gravity data. A massive impact redistributes internal mass, potentially altering the planet's moment of inertia. Spacecraft tracking allows estimation of gravity field variations. The moment of inertia factor provides clues about how mass is distributed between core and mantle. If Venus experienced a collision that significantly altered its interior structure, subtle deviations might appear in gravity harmonics. So far, gravity measurements derived from spacecraft such as Magellan suggest a differentiated planet with a metallic core and silicate mantle, broadly similar to Earth. No clear anomaly demands an extreme collision scenario, but measurement precision leaves room for refinement. Another expectation concerns satellites. A giant impact might produce debris capable of forming a moon, as occurred with Earth. Venus has no large natural satellite. Does this absence argue against the impact hypothesis? Not necessarily. The outcome of a collision depends sensitively on impact angle, velocity, and relative masses. Simulations indicate that some collisions may not leave stable debris disks. Material could reaccrete onto the planet or escape entirely. The absence of a moon does not decisively reject the model, but it reduces the parallels with Earth's history. Comparisons with other planetary impacts provide context. Studies of planetary accretion using high-resolution simulations show that large impacts were common during the first 100 million years after formation. These collisions often reshaped spin states. Some terrestrial planets could have experienced multiple large impacts before settling into their present configurations. In this chaotic environment, Venus may have undergone a late oblique strike that slowed and reversed its rotation. The mechanism fits within known processes, yet the geology of Venus raises additional questions. Impact craters observed by Magellan number roughly 1,000 across the planet. Their distribution suggests a surface age younger than many ancient terrains on Mars or Mercury. If a giant impact occurred early, it likely preceded this resurfacing epoch. In that case, the evidence would be buried beneath younger volcanic layers. Detecting remnants would require probing beneath the surface through seismic or high-resolution gravity measurements. The next generation of missions aims to provide such data. NASA describes its upcoming exploration in transformative terms, stating, "It will be as if we have rediscovered the planet." Missions such as Veritas and Da Vinci are designed to refine gravity field maps and atmospheric composition profiles. Higher resolution radar imaging may reveal tectonic features indicative of ancient structural disruption. Improved moment of inertia measurements could constrain interior layering with greater accuracy. The investigation continues. There is also a dynamical counter-argument. Some rotational models demonstrate that Venus's present spin state could arise without a single catastrophic event. Competing torques from solar tides and atmospheric thermal tides can gradually alter rotation over billions of years. If gradual torques suffice, the need for a giant impact diminishes. The challenge lies in distinguishing between an abrupt reversal early in history and a slow evolution driven by persistent forces. If a giant impact occurred, it would have deposited immense energy into the planet's mantle, potentially triggering long-lasting magma oceans or altering core formation processes. Geochemical analysis of atmospheric composition might preserve indirect clues. Venus's atmosphere is dominated by carbon dioxide, with trace noble gases that can record early degassing histories. Precise isotopic measurements may one day reveal whether the planet experienced unusually energetic early heating events. Atmospheric chemistry becomes part of the forensic toolkit. Researchers also examine angular momentum budgets statistically. In simulation ensembles of planetary formation, some planets naturally emerge with retrograde rotation due to stochastic collisions. Venus's retrograde state may simply represent one branch of probability among many outcomes. The solar system appears orderly now, but its infancy was marked by repeated high-energy interactions. Retrograde rotation is rare among the major planets, yet not impossible within formation models. The absence of visible bruises on Venus does not invalidate the impact scenario. It emphasizes the difficulty of reconstructing early history on a geologically active world. Surface renewal can conceal ancient trauma. The real record may lie in gravitational harmonics, interior density distribution, and isotopic fingerprints. Planetary science often advances by ruling out inconsistencies rather than proving singular events. What strengthens the inquiry is the interplay between models and measurement. Simulations predict outcomes under varying collision parameters. Observations constrain allowable histories. As data improve, some scenarios narrow while others gain plausibility. No definitive scar has been identified that demands a giant impact to explain Venus's rotation. At the same time, no dataset definitively excludes such an event. The hypothesis of a Mars-sized impact remains physically viable. The geological record remains ambiguous. The gravity field provides partial but not decisive constraints. The absence of a moon reduces certain parallels, but does not eliminate the possibility. The resurfaced terrain obscures direct evidence. The case remains open. As gravity data and measurements of Venus's internal structure grow more precise, the picture becomes clearer but also more demanding. Each refinement narrows the range of possibilities and places greater weight on processes acting at the surface and in the atmosphere. That focus brings renewed attention to a remarkable possibility. Could sunlight and moving air, acting over immense spans of time, gradually reshape a planet's rotation? Can sunlight and air slowly reverse a planet? How do atmospheric tides create torque? If no visible scar proves that Venus was struck hard enough to flip its spin, could something as ordinary as sunlight and air accomplish the same result over billions of years? At first glance, the idea seems insufficient. Venus has a mass of about 4.87 times 10 to the power of 24 kilograms. Its radius exceeds 6,000 kilometers. Its rotational inertia is immense. And yet, models developed by Alexandre Correa and Jacques Lascar show that persistent atmospheric tides, driven by solar heating in a thick atmosphere, can apply a long-term torque capable of altering rotation towards specific stable outcomes, including retrograde motion. The force is not dramatic. The duration is. To understand this mechanism, we begin with the concept of tides, not in oceans, but in atmospheres. On Earth, the Moon's gravity produces ocean tides. On Venus, the Sun exerts gravitational tides on the solid body. But Venus also experiences thermal tides. When sunlight heats one hemisphere more strongly than the other, atmospheric pressure redistributes. The heated air expands, forming a pressure bulge that is not perfectly aligned with the line connecting Venus and the Sun. Because of atmospheric inertia and frictional effects, this bulge is shifted slightly east or west of the subsolar point. That offset matters. Whenever mass is displaced from perfect symmetry relative to a gravitational source, torque arises. The Sun pulls on the atmospheric bulge. If the bulge is shifted ahead or behind the subsolar line, the gravitational pull exerts a twisting influence on the planet. Over a single day, the effect is extremely small. Over millions of years, it accumulates. Over billions, it becomes decisive. This is the central insight of the Correa and Lascar framework. Venus provides ideal conditions for strong thermal tides. Its atmosphere is composed primarily of carbon dioxide, with a surface pressure around 92 times that of Earth. Solar radiation heats the upper layers, creating temperature contrasts between day and night sides. Unlike Earth, where oceans and faster rotation distribute heat efficiently, Venus rotates slowly and maintains a dense atmospheric column. The resulting thermal bulges are substantial in mass compared to Earth's atmosphere. Greater mass means greater torque potential. Correa and Lasker constructed detailed dynamical models that incorporated gravitational solar tides, atmospheric thermal tides, internal friction, and planetary inertia. Their results showed that, under plausible parameters for Venus's atmospheric density and solar flux, the combined torques could drive the planet's rotation away from its initial prograde state. The system evolves toward equilibrium points where competing torques balance. For Venus, one such equilibrium corresponds to slow retrograde rotation close to the currently observed value. No collision is required. The explanation can be followed step by step without equations. First, solar heating produces atmospheric expansion. Second, expansion shifts mass distribution relative to the Sun. Third, the Sun's gravity pulls unevenly on that displaced mass. Fourth, the resulting torque modifies the planet's spin. Finally, internal and atmospheric friction determine how efficiently angular momentum is exchanged between atmosphere and solid body. Each step is measurable and grounded in known physics. Evidence for atmospheric dynamics on Venus comes from spacecraft observations. The European Space Agency's Venus Express mission measured global wind patterns and confirmed the presence of superrotation in the upper atmosphere, where winds can exceed 100 meters per second and circle the planet in about 4 Earth days. These fast-moving layers contain angular momentum that can couple to the surface through pressure gradients and turbulent mixing. When atmospheric circulation varies, the torque applied to the surface can change accordingly. The atmosphere is not passive. NASA's planetary science resources describe Venus as a world where the atmosphere rotates much faster than the surface. This mechanical difference between sky and ground establishes the foundation for torque exchange. If the atmospheric bulge consistently leads or lags solar alignment, the Sun's gravitational pull on that bulge produces a steady twisting effect. Over geological timescales, such bias can overcome the braking influence of solid-body solar tides, which by themselves would tend to slow rotation toward synchronous locking. A crucial aspect of the model involves competing torques. Solid-body tides raised by the Sun in the rocky interior attempt to reduce rotation speed and align the same face toward the Sun, similar to the Moon's relationship with Earth. Thermal atmospheric tides, however, can oppose that trend. Under certain atmospheric densities and rotation rates, the atmospheric torque becomes strong enough to balance or even dominate the solid-body tidal torque. When this happens, the system settles into a stable state where neither torque completely prevails. Stability emerges from balance. The timescale of this evolution is central to its plausibility. Correa and Lascar's calculations indicate that the transition to a stable retrograde state could occur over hundreds of millions to billions of years. That duration aligns with the age of the solar system. Unlike an impact, which would produce immediate change, atmospheric tides operate continuously. The torque never ceases as long as solar heating persists and the atmosphere remains dense. Persistence substitutes for violence. One might ask whether the atmosphere could have been dense enough in the early history of Venus to sustain such torques. Geological and atmospheric models suggest that Venus may have retained a thick carbon dioxide atmosphere for most of its history. The absence of large oceans means that surface heat distribution differs markedly from Earth's. Measurements of isotopic ratios in the atmosphere indicate significant atmospheric loss processes, but not the removal of the dense carbon dioxide envelope itself. A long-lived thick atmosphere strengthens the case for thermal tidal influence. The mathematics of angular momentum conservation supports this view. Angular momentum can be transferred internally between atmosphere and solid body without violating conservation laws. External torque from the Sun provides a net change in the system. The rate of change depends on the magnitude of the atmospheric bulge and the degree of phase offset. The slow rotation of Venus amplifies the effect because small torques produce relatively larger proportional changes in spin when baseline rotation is already weak. Slow systems are easier to redirect. The interplay between atmospheric tides and solar gravitational tides also explains why Venus did not become tidally locked in a simple one-to-one resonance. If only solid body tides acted, Venus might show the same face to the Sun as the Moon does to Earth. Instead, the competition between torques allowed a different equilibrium to emerge. The resulting rotation period of about 243 Earth days is not arbitrary. It corresponds to a stable point predicted by models incorporating atmospheric mass, solar flux, and internal dissipation factors. Observational support extends indirectly through measurements of rotational variability. Radar speckle tracking studies led by Jean-Luc Margot demonstrate that the length of Venus's day can vary by minutes due to atmospheric angular momentum exchange. This present-day variability confirms that the atmosphere remains capable of exerting measurable torque. If it can adjust rotation slightly over years, it could plausibly have altered rotation substantially over billions of years. The mechanism is active today. No single measurement confirms the full evolutionary pathway. Instead, a convergence of modeling, atmospheric data, and rotation measurements builds the case. Computer simulations reproduce retrograde end states under realistic atmospheric conditions. Spacecraft confirm dense atmospheric dynamics. Radar observations detect ongoing rotational adjustment. Each piece reinforces the plausibility of the atmospheric tide hypothesis. The elegance of the mechanism lies in its simplicity. Solar heating, pressure gradients, gravity, and friction are familiar forces. They operate continuously. Under the right configuration, their cumulative effect can redirect a planet's spin without requiring catastrophic impact. The idea does not exclude the possibility of past collisions. It demonstrates that they are not strictly necessary. Future missions promise tighter constraints. NASA describes upcoming exploration efforts with anticipation, noting that new radar mapping and gravity field data will reveal whether Venus is geologically active today. Improved knowledge of interior structure will refine torque models. If the moment of inertia factor and internal dissipation parameters become better constrained, the range of possible rotational histories will narrow. The case for atmospheric tides does not rest on speculation. It rests on physical principles verified on Earth and applied quantitatively to Venus. The conclusion remains open to refinement, yet the model's coherence is compelling. Heat redistributes mass. Mass offset creates torque. Torque alters spin. Over billions of years, the direction of rotation can change. Gradual forces can yield dramatic outcomes. The realization that sunlight and atmospheric motion can steadily compete with gravitational locking changes the balance of the argument. If these forces are capable of altering rotation over immense timescales, then tidal locking is no longer an automatic outcome. That shift brings us to a crucial comparison. Why did the Moon become tidally locked to Earth, while Venus did not settle into the same state? If tides can flip Venus, why didn't Venus become tidally locked like the Moon? Gravity is remarkably efficient at forcing close worlds to show the same face to their star, yet Venus refuses to freeze into that simple configuration. The Moon is tidally locked to Earth. Mercury sits in a stable 3:2 resonance with the Sun. Many exoplanets discovered close to their stars are expected to rotate synchronously. Venus orbits the Sun at about 108 million kilometers, closer than Earth, and over 4.5 billion years, solar tides have had ample time to act. Why does Venus still rotate at all? The answer begins with solid body tides. When the Sun's gravity pulls on Venus, it does not act equally on every part of the planet. The near side experiences a slightly stronger pull than the far side. This differential force stretches the planet slightly along the line pointing toward the Sun, creating tidal bulges in the solid body. Because Venus rotates, those bulges are not perfectly aligned with the Sun's direction. Internal friction within the planet's mantle causes the bulges to lag behind the exact Sun-planet line. That misalignment produces torque. Over time, the torque acts to slow rotation and drive the planet towards synchronous locking, where one rotation equals one orbital period. If only solid body tides operated, Venus would likely have approached synchronous rotation long ago. The strength of tidal braking depends on planetary structure, distance from the Sun, and internal dissipation. Venus's proximity to the Sun enhances tidal forces. Over billions of years, even small torques accumulate. The expectation from classical tidal theory is clear. Close terrestrial planets should tend towards synchronous states. Venus is close enough that this outcome seems reasonable. Yet observations show a different state. Venus rotates retrograde with a sidereal period of about 243 Earth days, while its orbital period is about 225 Earth days. It is not locked. It is not in a simple resonance like Mercury. Instead, it occupies a slow retrograde configuration that appears stable over geological timescales. This state requires explanation beyond solid body tides alone. The key lies in competing torques. As discussed in previous analyses by Alexandra Correa and Jacques Lascar, Venus's dense atmosphere introduces thermal atmospheric tides that act in opposition to solid body tides. Solar heating produces pressure bulges in the atmosphere that are slightly offset from the subsolar point due to thermal inertia and atmospheric dynamics. The Sun's gravitational pull on these displaced atmospheric masses creates torque that can accelerate or decelerate rotation depending on phase alignment. Unlike solid body tides, which consistently break rotation towards synchrony, thermal atmospheric tides can push in the opposite direction under certain conditions. When these opposing torques balance, the planet reaches an equilibrium rotation state. In this state, the net torque is approximately zero. The rotation persists not because tides are absent, but because they cancel. Venus may represent precisely such a balance point. To appreciate this, consider angular momentum exchange in simple terms. Solid body tides convert rotational energy into heat within the planet's interior, gradually slowing spin. Atmospheric tides, driven by sunlight, redistribute mass and can transfer angular momentum back to the solid planet. When atmospheric torque equals the braking torque from solid tides, rotation stabilizes. The resulting equilibrium may correspond to a rotation period close to what we observe today. This is not coincidence. It emerges naturally from the physics of mass distribution and gravitational interaction. Evidence that Venus's atmosphere is capable of exerting measurable torque exists in present-day rotation variability. Radar speckle tracking studies led by Jean-Luc Margot reveal that the length of the Venusian day can vary by about 20 minutes over time. These variations are attributed to exchange of angular momentum between atmosphere and solid body. If atmospheric processes can shift rotation measurably over years, their cumulative effect over billions of years is substantial. The mechanism is active, not theoretical. The equilibrium concept also explains why Venus's rotation is slow but not perfectly locked. If atmospheric torque were absent, solid tides would continue to reduce spin until one hemisphere permanently faced the Sun. If atmospheric torque were overwhelmingly dominant, rotation might accelerate or settle into a different resonance. Instead, the two influences counterbalance near the current retrograde period. Stability arises because small deviations from equilibrium generate restoring torques. If the planet rotates slightly faster, atmospheric torque changes phase and nudges it back. If it rotates slightly slower, solid body tides adjust the balance. The state is stable enough to last, yet sensitive enough to vary. Comparative planetology strengthens this view. Mercury, lacking a dense atmosphere, experienced primarily solid body tidal effects and settled into a 3:2 resonance with the Sun. The Moon, similarly devoid of atmosphere, is locked to Earth. Venus differs because of its massive atmospheric envelope. Its surface pressure is about 92 times that of Earth. High-altitude winds circulate rapidly, storing significant angular momentum. These characteristics fundamentally alter tidal evolution. Computer simulations of tidal evolution demonstrate multiple possible end states depending on atmospheric mass and thermal properties. Correa and Lascar's models show that, for a planet with Venus's parameters, stable retrograde rotation is a plausible attractor state. The planet's path through rotational history depends on initial spin rate, atmospheric density, and internal dissipation. Over time, the system evolves toward equilibrium. The mathematics describe basins of attraction rather than a single inevitable outcome. Observations of exoplanets offer additional perspective. Many close-in exoplanets likely experience strong stellar tides. Some are predicted to be tidally locked. However, those with substantial atmospheres may exhibit more complex rotational states. Venus serves as a local example that atmospheric tides can significantly modify simple tidal locking expectations. This insight influences interpretation of exoplanet climate models and habitability studies. The stability of Venus's current rotation does not imply permanence in an absolute sense. Gradual changes in atmospheric mass or solar luminosity could shift the equilibrium over geological timescales. The Sun's luminosity has increased slowly since the early solar system. Changes in atmospheric composition could alter thermal tide strength. The equilibrium point might migrate accordingly. The present state reflects a balance under current conditions. Spacecraft observations contribute essential constraints. The European Space Agency's Venus Express mission measured atmospheric circulation patterns and temperature distributions that inform thermal tide modeling. Gravity data from past missions constrain interior structure and tidal dissipation factors. Each dataset narrows uncertainties in the torque balance calculation. While precision remains imperfect, the convergence of modeling and observation supports the competing torque hypothesis. NASA planetary science communications often emphasize that Venus challenges simple analogies with Earth. Its rotational behavior exemplifies this challenge. A world similar in size and bulk composition to Earth exhibits a radically different spin state. The difference arises not from exotic physics, but from variations in atmospheric mass, solar heating, and tidal interactions. Ordinary forces, applied persistently and in opposition, produce a configuration that appears unusual but remains mechanically consistent. The equilibrium model also explains why Venus is not drifting steadily towards synchrony today. If net torque were negative, rotation would continue slowing measurably. Current measurements show variability, but no clear monotonic trend toward locking. This suggests the planet resides near a torque balance point. Minute fluctuations in atmospheric circulation temporarily shift rotation rate, yet the long-term average remains close to the observed value. Venus thus illustrates that tidal locking is not inevitable, even for close-in terrestrial planets. The presence of a massive atmosphere modifies the standard narrative. Solid tides and thermal tides interact. The final spin is not an endpoint imposed by a single force. It is a negotiated settlement between competing influences. The balance between solid tides and thermal tides can maintain an equilibrium rotation that is far more complex than simple gravitational locking. When those competing forces are taken seriously, the atmosphere itself moves to the center of the explanation. Its behavior is not a minor detail, but a dominant factor, especially on a planet where the air can circulate faster than the surface beneath it. Why does Venus's atmosphere lap the planet-what engine drives superrotation? If the solid surface of Venus requires about 243 Earth days to complete one rotation, how can the cloud tops race around the planet in roughly 4 Earth days? That contrast is not a minor irregularity. It is a dynamical statement about angular momentum, energy transport, and atmospheric coupling on a global scale. The surface moves slowly, almost reluctantly. The upper atmosphere moves with sustained velocity that can exceed 100 meters per second, near 60 to 70 kilometers above the surface. The difference demands explanation grounded in physics. The phenomenon is called superrotation. It refers to an atmosphere whose zonal winds move faster than the rotation of the underlying planet. Venus provides the clearest example in the solar system. Spacecraft observations beginning with the Soviet Venera missions and later refined by NASA's Pioneer Venus and the European Space Agency's Venus Express confirmed that the cloud layer at about 65 kilometers altitude completes a full circuit in approximately 4 Earth days. Measurements from Venus Express tracked cloud features in ultraviolet wavelengths and revealed persistent high-speed circulation patterns. These are not transient gusts. They are a global system. To understand how this is possible, one must follow angular momentum. The total angular momentum of the planet, atmosphere system must be conserved unless external torques act. The Sun provides gravitational torque, but within the Venus system, angular momentum can shift between layers. If the atmosphere accelerates relative to the surface, momentum must be redistributed. The question becomes how momentum is transported from one region to another and how it is maintained against frictional loss. Venus receives intense solar radiation. Because its rotation is slow, one hemisphere remains exposed to sunlight for extended durations. The upper atmosphere absorbs solar energy efficiently. This heating establishes strong temperature gradients between equatorial and polar regions and between day and night hemispheres. Such gradients drive circulation. Air heated near the equator rises, moves poleward at high altitude, cools, and sinks at higher latitudes. This pattern resembles a Hadley circulation cell, but on Venus, it can extend nearly from equator to pole due to the planet's slow spin. The geometry of rotation matters. On a rapidly rotating planet like Earth, Coriolis forces break circulation into multiple cells. On Venus, the weak Coriolis effect allows large-scale meridional flows. These flows transport angular momentum from equatorial regions, where atmospheric parcels already possess higher tangential velocity due to planetary rotation, toward higher latitudes. When air moves poleward while conserving angular momentum relative to the planet's axis, it can accelerate eastward relative to the surface. Over time, this mechanism contributes to enhanced zonal winds. However, large-scale circulation alone cannot fully account for the magnitude of superrotation. Planetary-scale waves also play a central role. Observations from Venus Express and Akatsuki, the Japanese Aerospace Exploration Agency mission, identified atmospheric waves propagating through the cloud layer. Some of these waves resemble Kelvin waves, which travel along the equator, while others resemble Rossby waves influenced by planetary rotation. These waves transport momentum horizontally and vertically. When waves break, they deposit momentum into the mean flow, accelerating zonal winds. This process can be described without equations. Energy injected by solar heating excites atmospheric motions. Some motions organize into waves. Waves carry momentum from regions where it is generated to regions where it is dissipated. When they interact with background winds, they can transfer that momentum, strengthening the overall circulation. Over time, this feedback supports persistent high-speed rotation in the upper atmosphere. Frictional coupling between atmosphere and surface moderates this system. Near the surface, wind speeds are relatively low due to drag against the rugged terrain. Radar mapping by NASA's Magellan mission revealed a surface covered with volcanic plains and deformed crustal structures. These features create roughness that slows near-surface winds. Yet above the boundary layer, friction decreases sharply. The atmosphere at cloud-top levels encounters minimal drag and can sustain high velocities with relatively modest energy input. The vertical structure is decisive. Momentum exchange between upper atmosphere and lower layers is mediated by turbulence and wave propagation. The fact that the upper atmosphere rotates much faster than the surface indicates that angular momentum is not evenly distributed. Instead, it is concentrated aloft. The mechanism resembles a flywheel effect, where energy stored in fast-moving upper layers can influence deeper regions through pressure gradients and wave-induced stresses. Data from the Japanese Aerospace Exploration Agency's Akatsuki spacecraft provided additional clarity. Akatsuki detected a stationary gravity wave structure above highland regions such as Aphrodite Terra. These stationary waves indicate strong coupling between surface topography and atmospheric flow. When winds pass over elevated terrain, they generate waves that propagate upward and can redistribute momentum. This observation confirms that surface features influence atmospheric dynamics despite the thick carbon dioxide envelope. NASA planetary scientists have emphasized that Venus's atmosphere behaves as a global circulation engine. The energy source is solar radiation. The working fluid is carbon dioxide mixed with clouds of sulfuric acid droplets. The mechanical output is sustained zonal wind. While Earth's jet streams are confined to mid-latitudes and vary seasonally, Venus's superrotation is nearly uniform and persistent. It is a planetary-scale circulation regime. One might ask whether superrotation feeds back into the planet's spin. Because the atmosphere carries angular momentum, changes in wind speed can exchange momentum with the solid body. Radar observations indicate that Venus's rotation rate varies by minutes, likely due to atmospheric angular momentum changes. This confirms that the atmosphere is not merely responding to planetary rotation. It is capable of influencing it. The exchange, though small in absolute terms, demonstrates mechanical coupling between sky and ground. The persistence of superrotation also depends on radiative balance. Venus's thick clouds reflect a large fraction of incoming sunlight, yet enough energy penetrates to sustain convection and circulation. The greenhouse effect traps infrared radiation, maintaining high temperatures of about 730 Kelvin at the surface. At cloud-top altitudes, temperatures are lower, enabling strong horizontal temperature gradients. These gradients sustain pressure differences that drive winds. Remove the thermal contrast, and superrotation would weaken. Comparative studies with Titan, Saturn's largest moon, show that superrotation can occur in other dense atmospheres under appropriate conditions. However, the magnitude on Venus remains the most extreme among terrestrial bodies. This suggests that slow planetary rotation, combined with dense atmosphere and strong solar heating, create optimal conditions for global-scale angular momentum redistribution. Computer simulations of Venusian atmospheric dynamics reproduce superrotation when they incorporate realistic radiative transfer and wave interactions. These simulations demonstrate that small imbalances in momentum transport can amplify through feedback loops. Once established, superrotation becomes self-sustaining as long as solar energy input continues. The existence of superrotation reinforces earlier discussions about competing torques. A fast-moving upper atmosphere enhances the effectiveness of thermal atmospheric tides. The displaced mass associated with pressure bulges depends on atmospheric circulation patterns. Therefore, superrotation is not isolated from rotational evolution. It is intertwined with it. The atmosphere does not simply respond to the planet's spin, it shapes it. Venus thus stands as a case study in coupled planetary dynamics. The slow rotation of the surface creates favorable conditions for large Hadley cells. Those cells, together with planetary waves, redistribute angular momentum. Upper-level winds accelerate dramatically. Frictional coupling allows exchange with the surface. Over geological time, such exchanges influence the planet's overall spin state. The surface moves slowly. The clouds move quickly. Between them lies a dynamic engine powered by sunlight and governed by fluid mechanics. Each measurement from spacecraft refines our understanding of how momentum travels through a planetary atmosphere. The atmosphere is not a passive blanket, it is an active dynamical system. Venus's atmosphere can move far faster than the planet's surface, completing a full circulation in just a few Earth days, while the ground rotates far more slowly. Such a dramatic difference forces a closer look at how energy is distributed across the planet. If the surface turns so gradually, one might expect scorching days and frozen nights, yet observations show something very different. Why is Venus almost the same temperature everywhere? Shouldn't slow rotation create extreme day-night contrast? If one hemisphere of Venus faces the Sun for months at a time, Why does the surface remain nearly the same temperature on the day side and the night side? A world that rotates once every 243 Earth days should, by simple expectation, bake under prolonged sunlight and then cool dramatically in extended darkness. Yet measurements from multiple missions show that Venus maintains a surface temperature close to 730 Kelvin across nearly all latitudes and longitudes. The contrast is not extreme, it is remarkably small. This uniformity is not accidental. It arises from a dense carbon dioxide atmosphere, approximately 92 times the surface pressure of Earth, and extending upward tens of kilometers. The greenhouse effect on Venus is not subtle. Solar radiation enters through the cloud layers, is absorbed by the surface, and re-emitted as infrared radiation. Carbon dioxide molecules absorb that infrared radiation efficiently. The energy becomes trapped within the lower atmosphere and is redistributed rather than escaping directly to space. NASA has described Venus as a planet where the greenhouse effect is runaway. That term refers to a feedback process in which warming increases atmospheric opacity to infrared radiation, which in turn enhances warming. However, beyond raising global temperature, this process also stabilizes temperature differences. A thick atmosphere with strong infrared absorption limits how quickly the surface can cool, even during long periods without direct sunlight. Thermal inertia becomes dominant. When sunlight heats the day side, the energy does not remain confined to that hemisphere. High-altitude winds transport heat efficiently around the planet. The superrotation of the upper atmosphere, completing a full circuit in roughly 4 Earth days, acts as a global conveyor. Energy absorbed at the day side is redistributed before significant cooling can occur on the night side. This atmospheric circulation effectively erases large-scale temperature contrasts. The physics of heat transport can be understood in simple terms. Warm air rises and moves horizontally at altitude. Because Venus rotates slowly, Coriolis forces are weak, allowing large-scale circulation cells to span broad latitudinal ranges. Air heated near the equator ascends and flows toward higher latitudes, then descends and returns toward the equator near the surface. This circulation distributes energy meridianally. Simultaneously, zonal winds carry heat longitudinally. The combined motion smooths gradients. Data from the Soviet Venera landers provided direct surface measurements, confirming temperatures near 730 Kelvin at different locations. Later, NASA's Magellan mission mapped surface features with radar, enabling correlation between topography and atmospheric behavior. More recently, the European Space Agency's Venus Express measured temperature profiles at various altitudes. These observations show that temperature variations at the surface are typically only a few degrees across the globe, despite enormous differences in solar exposure duration. One might compare this with the Moon. The Moon lacks a substantial atmosphere. During its 2-week-long lunar day, temperatures can exceed 390 Kelvin. During its equally long night, temperatures can drop below 100 Kelvin. The absence of atmospheric heat transport permits extreme contrast. Venus, in contrast, is enveloped in a dense atmospheric blanket that redistributes energy continuously. Atmosphere changes everything. The greenhouse effect also shifts the altitude at which radiation escapes to space. On Venus, outgoing infrared radiation originates from high cloud tops where temperatures are significantly lower than at the surface. This radiative level acts as a thermostat. Because radiation escapes from similar altitudes globally, and because upper atmospheric temperatures vary less dramatically than surface exposure might suggest, global energy balance remains relatively uniform. Venus's clouds, composed of sulfuric acid droplets, reflect a large fraction of incoming solar radiation. The albedo of Venus is high, meaning much sunlight is reflected back into space. This limits the amount of energy reaching the surface directly. Yet the energy that does penetrate becomes trapped efficiently. The system reaches radiative equilibrium at a high temperature that is nearly constant across the planet. The connection to rotational dynamics becomes clear when considering atmospheric tides. The same dense atmosphere responsible for uniform temperature also generates thermal bulges that influence torque. If the atmosphere were thin, day-night temperature contrasts would be greater, but thermal tides would be weaker. Instead, the thick atmosphere creates strong pressure variations driven by solar heating. These pressure variations shift mass distribution relative to the Sun and contribute to the torque balance discussed earlier. Climate and spin are intertwined. Consider how slowly Venus rotates relative to its atmospheric circulation. A point on the surface remains illuminated for months, yet the atmosphere above it circulates dozens of times during that period. Heat does not remain stationary above a single region. Instead, the fast-moving upper atmosphere ensures that absorbed solar energy is mixed globally long before the surface completes a fraction of its rotation. Thermal diffusion within the dense lower atmosphere further suppresses temperature contrast. Because the atmosphere is thick and composed primarily of carbon dioxide, its capacity to store heat is substantial. Energy absorbed during daylight persists in the atmospheric column and radiates slowly. Even when a region enters night, it continues to receive downward infrared radiation from warmer layers above. Cooling is gradual and limited. The pressure at the surface, about 9 million pascals, enhances the greenhouse effect by broadening absorption lines of carbon dioxide. This pressure broadening increases the efficiency with which infrared radiation is trapped. The result is not only elevated temperature, but also uniformity. Regions of the planet cannot radiate heat away rapidly enough to create sharp gradients. Venus Express also detected minor variations in cloud top temperatures correlated with atmospheric waves and circulation patterns. These variations, however, remain modest compared to what slow rotation alone would predict. The circulation regime dominates over radiative contrast driven purely by geometry. Comparative climate models reinforce this understanding. Simulations of slowly rotating exoplanets with dense atmospheres often show efficient redistribution of heat, leading to small day-night contrasts. The case of Venus provides empirical validation of these models. A thick atmosphere, coupled with strong zonal winds, can override the geometric expectation of extreme thermal asymmetry. The implication for rotational evolution is direct. The thermal structure that minimizes temperature contrast also establishes the pressure gradients responsible for atmospheric tides. Uniform high temperature does not mean absence of dynamical complexity. On the contrary, the climate engine of Venus produces both superrotation and torque. Stability at the surface coexists with motion above. This coupling means that any change in atmospheric density or composition could alter both temperature distribution and rotational torque. If atmospheric mass decreased significantly, greenhouse trapping would weaken, temperature contrasts would increase, and the balance of tidal torques could shift. Conversely, increased atmospheric opacity would further stabilize thermal uniformity while modifying pressure bulges. Venus therefore demonstrates that planetary rotation, atmospheric circulation, and radiative transfer form a tightly linked system. The planet's nearly uniform temperature is not a passive outcome. It is an emergent property of atmospheric dynamics operating under intense solar heating and high pressure. Surface probes have confirmed that despite variation in altitude and latitude, temperatures remain clustered near 730 Kelvin. Highlands such as Maxwell Montes are slightly cooler due to elevation, yet the differences remain small compared to lunar or Martian extremes. The atmosphere enforces global coherence. When considering the broader rotation mystery, it becomes clear that climate cannot be separated from mechanics. The dense carbon dioxide atmosphere that traps heat also redistributes angular momentum and shapes tidal torques. The physical processes responsible for uniform temperature simultaneously influence spin stability. Venus does not exhibit extreme thermal contrast because its atmosphere acts as a global heat exchanger. Solar energy absorbed at one location is shared with the entire planet before significant radiative loss occurs. The result is a surface environment that remains uniformly hot regardless of longitude. Venus is wrapped in a dense greenhouse envelope that controls both heat transport and the generation of atmospheric torque. When a single system governs so much of a planet's behavior, its consequences cannot remain confined to temperature and rotation alone. That broader impact raises a critical possibility. If Venus spins slowly and lacks a strong internal dynamo, could this be why it does not possess a global magnetic shield? And could that long-term exposure have permanently altered its atmosphere? Did Venus lose its magnetic shield because it spins too slowly, and did that exposure reshape its atmosphere forever? If a planet nearly identical to Earth in size and bulk composition lacks a strong global magnetic field, what does that absence reveal about its interior, its rotation, and its atmospheric history? Venus and Earth formed from similar building blocks, both likely developed metallic cores rich in iron and nickel. Yet Earth possesses a powerful magnetic field generated by a dynamo in its liquid outer core, while Venus shows no comparable global magnetosphere today. The difference is not trivial. It alters the long-term interaction between planet and star. A planetary magnetic field arises from motion within an electrically conducting fluid. On Earth, convection in the liquid outer core, combined with planetary rotation, organizes fluid motion into patterns that sustain a global magnetic field. The rotation of Earth, once every 24 hours, enhances the alignment of convective currents through the Coriolis effect. This organized motion enables a dynamo mechanism. The magnetic field extends outward into space, deflecting charged particles from the solar wind and forming a magnetosphere. Venus rotates once every 243 Earth days, and it rotates retrograde. Such slow rotation weakens the Coriolis effect in the core. If convection exists, it may not organize into the coherent, columnar structures necessary for sustaining a strong global dynamo. Models of planetary magnetism suggest that rotation rate influences the geometry and intensity of magnetic field generation. A slowly rotating core may still convect, but without sufficient rotational influence, large-scale field coherence may not emerge. Rotation shapes magnetism. Spacecraft measurements confirm that Venus lacks a significant intrinsic dipole magnetic field. Data from NASA's Pioneer Venus mission, and later from the European Space Agency's Venus Express, show only an induced magnetosphere created by the interaction of the solar wind with the upper atmosphere. The magnetic field observed near Venus arises primarily from currents induced in the ionosphere not from a self-sustaining internal dynamo. The contrast with Earth is measurable and persistent. Without a robust intrinsic magnetic shield, the solar wind interacts more directly with Venus's upper atmosphere. The solar wind consists of charged particles streaming outward from the Sun at speeds of hundreds of kilometers per second. When these particles encounter a planetary atmosphere, they can transfer energy and momentum. On Earth, the magnetosphere deflects most of this flow. On Venus, the atmosphere itself acts as the obstacle. Over long timescales, solar wind interaction contributes to atmospheric escape. Charged particles can accelerate atmospheric ions to velocities sufficient to overcome gravitational binding. Observations by Venus Express detected streams of oxygen and hydrogen ions escaping from the upper atmosphere. These measurements indicate that Venus continues to lose atmospheric particles today, although at a relatively modest rate compared to early solar conditions. The ratio of deuterium to hydrogen in Venus's atmosphere provides further evidence of significant water loss in the past. Deuterium is a heavier isotope of hydrogen. Because lighter hydrogen escapes more readily to space, an elevated deuterium to hydrogen ratio implies that substantial quantities of hydrogen were lost over time. Current measurements show that Venus's deuterium to hydrogen ratio is about 100 times that of Earth's oceans. This suggests that Venus may once have possessed more water than it does today. The atmospheric record preserves memory. The absence of a strong magnetic field may have contributed to this history. Early in the solar system, the Sun was more active and emitted stronger solar wind flux. A planet lacking magnetic protection would have experienced more intense atmospheric stripping. Over hundreds of millions of years, cumulative escape could remove lighter elements, including hydrogen derived from water vapor. Rotation, however, is not the sole determinant of dynamo action. Internal heat flow, core composition, and mantle convection also play critical roles. Venus may have a liquid outer core similar to Earth's. Yet if internal heat loss is slower due to differences in mantle dynamics or absence of plate tectonics, convection patterns in the core could differ substantially. Some geophysical models suggest that Venus's mantle may operate in a stagnant lid regime rather than active plate tectonics, limiting efficient heat transfer from the interior. Reduced heat flow may weaken core convection, further diminishing dynamo potential. The link between rotation and dynamo efficiency remains an active area of research. Laboratory and numerical simulations show that faster rotation tends to promote organized magnetic fields, but slow rotation does not guarantee absence of magnetism. It alters the geometry and intensity. For Venus, the combination of slow rotation and possible reduced core convection likely suppresses a strong dipole field. The consequences extend beyond atmospheric escape. A magnetosphere influences how energy from the solar wind couples to the atmosphere. On Earth, magnetic reconnection events drive auroras and deposit energy at high latitudes. On Venus, without a global field, energy deposition occurs more directly in the upper atmosphere, potentially affecting chemical reactions and ionization patterns. Venus Express measurements revealed an induced magnetotail extending downstream of the planet, shaped by solar wind interaction. This induced structure provides some shielding but lacks the stability and strength of an intrinsic magnetic field. It fluctuates with solar activity. During periods of heightened solar wind pressure, atmospheric escape rates increase. The long-term climatic implications are significant. Loss of hydrogen over geological timescales would reduce water content irreversibly. Without substantial water, Surface processes and chemical cycles differ from Earth's. Carbon dioxide accumulates in the atmosphere rather than being sequestered in oceans and carbonate rocks. The greenhouse effect intensifies. Surface temperatures rise to approximately 730 Kelvin. Interior dynamics, rotation, and atmosphere converge. The connection between spin and fate thus becomes clearer. Slow rotation may weaken dynamo efficiency. A weak or absent magnetic field permits stronger solar-wind interaction. Enhanced atmospheric escape contributes to long-term compositional evolution. Meanwhile, greenhouse warming, driven by retained carbon dioxide, establishes extreme surface conditions. These processes reinforce one another through feedback. Yet caution is necessary. Some models propose that even with a magnetic field, atmospheric escape could still occur under intense early solar conditions. Earth itself has lost atmospheric particles despite its magnetosphere. Therefore, absence of magnetism is not the sole factor in Venus's evolution. It is one component in a multifaceted system. Future missions may clarify the state of Venus's interior. Measurements of the planet's moment of inertia and gravity field can constrain core size and density. Improved understanding of mantle convection patterns will inform dynamo modeling. NASA describes upcoming exploration efforts as transformative, stating that new missions will help determine whether Venus is geologically active today. If active volcanism persists, internal heat flow may be more complex than currently understood. The question of habitability arises indirectly. Earth's magnetic field is often cited as protective, preserving atmosphere and water over billions of years. Venus offers a counterexample that emphasizes sensitivity to multiple parameters, including rotation rate, distance from the Sun, atmospheric composition, and interior dynamics. Slight differences in initial conditions may lead to divergent outcomes. Venus's slow spin, lack of strong magnetic shield, and extreme greenhouse climate form an interconnected narrative. The rotational state influences dynamo behavior. Dynamo behavior influences atmospheric retention. Atmospheric evolution influences surface temperature and climate stability. The chain is continuous. Present measurements confirm that Venus does not generate a strong intrinsic magnetic field. Solar-wind interaction shapes its upper atmosphere directly. Atmospheric escape processes operate measurably today. The high deuterium to hydrogen ratio signals substantial past water loss. Each dataset contributes a piece to the planetary history. Spin rate, interior convection, magnetic shielding, and atmospheric escape are not isolated processes. Across billions of years, they interact as parts of a single planetary system, each influencing the others. When so many mechanisms are entangled, only precise measurements can untangle their relative roles. That is why the next step depends not on speculation, but on new data capable of testing these competing explanations. What measurement will finally break the case are we about to rediscover Venus with new missions? If decades of radar echoes and atmospheric models have brought us this far, what single measurement could finally decide whether our theories about Venus stand firm or quietly fall apart? Beneath the thick clouds, beneath the volcanic plains mapped in the 1990s by NASA's Magellan spacecraft, lies a set of unknowns that no spacecraft has yet resolved with precision. The gravity field is not mapped in fine detail. The interior mass distribution remains uncertain. The moment of inertia is constrained only within broad limits. The resurfacing history of the crust is debated. And each of these unknowns connects directly to the story of spin, atmosphere, and fate. The gravity field of a planet is not merely a measure of mass, it is a map of how that mass is distributed inside. When a spacecraft orbits Venus, tiny variations in gravitational pull slightly alter its trajectory. By tracking the spacecraft's radio signal with extreme precision, scientists can reconstruct these variations. From them, they infer whether mass is concentrated toward the center or distributed differently within mantle and crust. A precise gravity field reveals clues about core size and density. Moment of inertia is especially decisive. In simple terms, it describes how resistant a planet is to changes in rotation. A planet with more mass concentrated toward its center has a lower moment of inertia factor than one with mass distributed farther outward. By measuring small variations in rotation rate and by observing how the planet responds to tidal forces from the Sun, scientists can estimate this parameter. Radar speckle tracking from Earth-based observatories has already provided constraints. Yet the uncertainty remains large enough that competing interior models still fit the data. Narrowing that uncertainty would immediately strengthen or weaken specific dynamo and tidal evolution scenarios. Surface mapping is equally critical. Magellan, operating between 1990 and 1994, used radar to penetrate Venus's clouds and produced global maps at resolutions of roughly 100 meters per pixel in many regions. Those images revealed vast volcanic plains, corona structures, and tectonic features. However, Magellan's data left open a major question about resurfacing. Did Venus undergo a catastrophic global resurfacing event hundreds of millions of years ago, or has volcanic activity been more continuous and localized? The answer influences internal heat flow models, which in turn affect predictions about core convection and magnetic history. NASA's upcoming mission Veritas, scheduled for launch no earlier than 2031, aims to improve radar resolution dramatically and refine gravity measurements. Veritas will carry a synthetic aperture radar system, capable of mapping surface features at much higher resolution than Magellan. It will also perform precise tracking to derive gravity field variations. According to NASA, it will be as if we have rediscovered the planet. That statement reflects not hyperbole, but the scale of improvement in measurement accuracy. Finer detail means fewer viable models. At the same time, the Da Vinci mission, planned for the early 2030s, will send a descent probe through Venus's atmosphere. As it falls, it will measure atmospheric composition with high precision. Ratios of noble gases and isotopes provide constraints on the planet's formation history and volatile evolution. The deuterium to hydrogen ratio already indicates significant water loss. Additional isotopic measurements may refine the timeline of atmospheric escape. By correlating atmospheric composition with surface chemistry observed during descent, scientists can link climate evolution with interior processes. A precise determination of spin state variability also matters. Radar observations have shown that Venus's day length can vary by minutes over time. Continued monitoring with improved instrumentation can measure these variations more accurately. Such measurements inform models of atmospheric angular momentum exchange and interior structure. If rotational variations correlate with specific atmospheric patterns, the coupling between sky and solid planet becomes clearer. The decisive dataset may not be a single number, but a coherent combination of gravity field, moment of inertia, spin variability, and high-resolution surface imaging. Each piece constrains the others. For example, if gravity data reveal a larger than expected core, dynamo models must account for it. If surface mapping identifies recent volcanic activity, internal heat flow estimates change. If atmospheric composition indicates prolonged volatile loss, interaction with solar wind must be quantified precisely. The system is interconnected. Earth-based radar studies have already demonstrated the power of remote measurement. Jean-Luc Margot and collaborators used radar speckle techniques to refine rotation period estimates and constrain interior properties. These results illustrate how small shifts in measured rotation translate into inferences about planetary structure. However, Earth-based observations are limited by distance and signal strength. Orbital missions provide continuous, high-resolution data that cannot be matched from Earth alone. The European Space Agency's experience with Venus Express revealed how even modest improvements in instrumentation can reshape understanding. Venus Express detected atmospheric waves, mapped temperature profiles, and measured atmospheric escape rates. Yet it did not carry advanced radar for surface mapping. The next generation of missions is designed specifically to close those gaps. A refined gravity map could determine whether mass anomalies correspond to active mantle plumes. If active plumes exist, Venus may still be geologically dynamic. That dynamism influences internal convection, which in turn affects any potential dynamo action. Similarly, improved knowledge of crustal thickness variations could reveal whether resurfacing was episodic or continuous. Each scenario implies different thermal histories. Precision is the central theme. When uncertainties shrink, theoretical flexibility narrows. Models that once seemed equally plausible begin to diverge under tighter constraints. Theories about atmospheric tides, equilibrium rotation, and magnetic field suppression will face quantitative tests rather than qualitative debate. Consider how a more accurate moment of inertia factor might influence conclusions. If measurements show that mass is more centrally concentrated than currently estimated, core size could be larger. A larger liquid core may enhance the possibility of past dynamo activity, even if none exists today. Alternatively, if mass distribution indicates a smaller or partially solidified core, dynamo scenarios weaken. A single parameter reshapes multiple narratives. Similarly, if Veritas mapping identifies signs of recent lava flows, interior heat flow remains active. Active volcanism may replenish atmospheric gases, affecting chemical balance and greenhouse dynamics. Such findings would refine estimates of atmospheric evolution and escape processes. The phrase "rediscovered the planet" reflects the recognition that Venus has not been observed with the resolution and precision applied to Mars or the Moon in recent decades. Advances in radar technology, gravity science, and atmospheric instrumentation promise a level of detail previously unavailable. The integration of atmosphere, surface, and interior data will allow consistent modeling rather than isolated hypotheses. Scientific progress often hinges on improved measurement rather than new speculation. When Galileo improved the telescope, the moons of Jupiter became visible. When radar mapping was first applied to Venus, its hidden surface emerged. The coming decade may offer similar transformation. The outcome will not simply refine numbers. It will determine whether the balance of torque's explanation remains robust. It will test whether slow rotation truly limited dynamo action. It will clarify whether resurfacing erased impact evidence or reflects ongoing internal processes. Each dataset reduces ambiguity. As exploration advances, the narrative of Venus becomes less about isolated mysteries and more about integrated planetary evolution. Spin, atmosphere, interior structure, magnetic shielding, and climate form a coherent system governed by measurable physics. The next wave of missions seeks not fragments, but consistency. If the new gravity maps, descent data, and rotation measurements match what our current models predict, then Venus becomes one of the clearest, best tested examples we have of how planetary dynamics plays out over deep time. If the numbers do not match, then the models will need to change carefully and with the same discipline we used to build them. Either way, the result is useful because it replaces assumptions with measurements. Thank you for giving your time to a topic this detailed. I know attention is valuable, and I don't take it for granted. If you'd like to support more work like this, a subscribe is a small action that makes a real difference for me and helps me keep making these long, careful explorations. And if you feel like sharing, tell me where you're listening from tonight, and anything you'd want improved or explained more clearly next time. I read those notes, and they genuinely shape what comes next.